Hey everyone, welcome to Devs in the Sheds. We've got Paul, Aaron, and myself on, the regular Dev Shedders. I'm traveling today, so I'm not in my sheds, and it's pretty cold in Melbourne overall. So I think we're a little more dev and a little less shed this week. But we are joined by a few people within AWS Melbourne offices by the looks of it. Patrick, starting with you, do you want to kind of go around the room and give everyone a quick introduction?
Yeah, sure. So my name is Patrick O'Connor. Second appearance with the Shedders. A little bit about myself. So I work at AWS as a developer under Proserv, so professional services. If I had to quickly describe what sort of work I do, in the field of consultancy, where I engage, talk strategy, talk build, and then I do quite a bit of coding as well. So quite a lot of proof of concepts and kind of a lot of building stuff. Yeah. So
nice. Ishan?
Well, I think that's a good way to summarize. Pat, hello everyone. I'm Ishan. Pat, Jeff, and I work in the same team in pretty much what Patrick described, but I do also enjoy mobile apps a lot and also tying that up with emerging technologies like AR, VR, and I've also been very much into machine learning these days as well. So that's pretty much a little bit about me. Over to you, Jeff.
Very cool. Yeah, Jeff.
Hey everyone, my name's Jeff Sang. Again, part of the customer intelligence team at Commercial Proserv. So I guess a little bit more about what our team does. We really focus on emerging tech. So our coverage is AI and ML, quantum computing, blockchain, and IoT. So within that, I'm an associate data scientist. So I primarily focus on AI and machine learning projects for our customers. But beyond just the dev work, at its core, we're all consultants. There's a lot of kind of working with customers to understand, their business problems and how we can build a tech solution to deliver value for them.
Very nice. And I know everyone's excited to hear about what we're presenting on today. There's a wide variety of skills. Like I know Patrick and Ishan from way back. Patrick even, I think it was we worked with each other at some university events and then some customers as well. But we've got a broad set of skills here, right? So we are going to have a look at some image recognition to do with counting objects within video footage, I think. So we're going to look at OpenCV today. We're going to have a look at some of the machine learning algorithms created around that. And then I think because we've got such a wide skill set here, an app was needed to be produced to use the machine learning models and actually show end users what the predictions are. So I think it's going to be going around the room, and I think there's going to be a little bit for everyone. I hope the whole audience is going good today. Feel free to jump on them with millions of questions. We've got three very smart people in the room. But before we actually have a look at the project that you've got, tell me a little bit more about Proserv, right? I think this is the first time, Patrick, we've had you on before, but this is the first time we've had a bunch of Proserv people on. I myself was a technical account manager. I'm now a developer. Paul and Aaron are solution architects in AWS. How does professional services fit in the picture? Because you guys, to me, are very, very hands-on directly with customers, building things for customers rather than just building things internally for customers. Kind of the same saying, but quite different, right? It's very specific customer use cases you're building for. Yeah.
Aaron and I will probably spend a good chunk of time building proof of concepts, working with a set of assigned accounts day to day. But we still have a significant amount of crossover with Proserv. But yeah, it's probably people do ask a lot of me what is the difference between a cloud architect and a solutions architect? So yeah, let's hear it from the mouth of Proserv itself.
Sure. Yeah. Do you want to tackle it, Jeff?
You take this one. So I guess in summary, we are the builders within Amazon's customer-facing business. So I guess if we could summarize the way that AWS will interact with customers, at the start, you have kind of sales teams who work with customers, build that relationship, and understand their business problems. And they might work with a solutions architect to understand what that solution may look like on the AWS platform. But then once that kind of solution is sold as a statement of work or a SOW, that then gets passed to either a partner within the Amazon Partner Network, or it comes to Proserv, which is kind of Amazon's internal function for building out solutions, for our customers. And so, what that process will look like typically is, start off with a proof of concept or proof of value, just to show, what could be done for the customer and how this could bring value to their business. And then if they wish to pursue that, we can build it all the way out to an MVP and then a full-scale production solution for them.
And you guys might do that for the customers sometimes, and then Paul or Aaron might do that for the customers sometimes, right? Depending on whether you guys are already hands-on with that customer, and depending on the scope or the size of things. Yep.
Exactly.
Cool. Yep. Very nice.
Yeah, I guess a couple of things. It's very hands-on, and it's also in different areas as well, particularly around problems that need solving quickly, or the skill sets to help accelerate the outcomes for the customer. So the focus with Proserv is delivering quickly and help the customers move a lot faster than they could with other options.
Yeah, I think Ishan puts it well as well. At the start, he was kind of mentioning that Proserv is quite a big umbrella. Just like in SAs, you've got SAs who work with startups, you've got SAs that work all the way up to enterprises. In professional services, you have same diversities. You've got commercial sector, you've got public sector, who are different customers, but then within those departments, you have subsections that focus on different types of priorities. So taking our team, for example, we work in the emerging practice. So a lot of our focus as professional services, a lot of the sort of engagements we're engaged for include new technologies around blockchain, AR, VR, machine learning is quite a big one that's prevalent in our team. But then on the other side, and we have quite a lot of teams within that team that focus on different stuff like data. And then on the other side of the department, you have core services that we're all still working technology, but their focus is on strategy, transformation, migration, still using the AWS platform, but their kind of focus within professional services is just a little bit different. So I guess like we all sum it up well in Proserv's about bringing rapid transformation to customers, very code intensive. So cloud architects might come onto an engagement and draft up a solution and help implement it, or they could go down to us, for example, where we're not just implementing it, but we're also coding the platform to help drive them forward using AWS.
And I think like there's one thing that you called out there a couple of times, and it would probably be good to just clarify and just go over that. So when we think about like AWS, yes, at AWS we have like infrastructure, we build code, we've got CloudFormation, and we're building solutions on AWS. Proserv doesn't just like build out infrastructure or CloudFormation or CDK to do that, or design your accounts. It can do all of those things, but also your teams are actually building the software that is being delivered to those customers. So specific and highly customized and tailored software that is being built and delivered for the customer. And I think that there's a number of arrangements there, whether or not that becomes shared or owned by the customer or co-owned all the way through. So you're actually building some piece of software to the customer rather than a piece of infrastructure or a design, passing that across. So it's very much like, for anybody that's, worked within a product team where you're building some application, whether it be like a real estate site or something like that, you're going into the customer and the customer has said, hey, we're a little down on resource or a little down on expertise around a certain area. We need somebody to bolster our development team and to go forward. So, and that probably comes back to what you guys have said. You are software engineers. So there's can be quite a significant difference between a solution architect and a cloud architect, because a cloud architect typically has a strong background in software engineering and is an actual software engineer, hands on the code.
Yeah. But I'd also say to that though, Paul, is the solution architects at AWS have been software engineers, and so they're not kind of like the architects that haven't touched code for a very long time, right? Like it's highly encouraged as an SA to keep hands on the coding skill sets, right? And it's kind of a requirement, because you're not just working with the customer architects, you're also working with engineering teams, and sometimes patterns in the industry that are advertised aren't the right fit for particular like requirements and use cases, right? And so you've got to have the skills to know when to propose an alternate route, right? To the customers.
I think also it depends on, like, for an insight into the world of AWS, it depends on really what team you're in, as in like the difference between Paul and I. Paul's in the accounts space, I'm in the partner space. I won't talk to what Paul does, but as a partner solutions architect, I am very much in the prototyping space. So I am writing code very often, but it's very much proof of concept. So I will help the partner who is working with a customer to then build a proof of concept. But then once we get from that, I will engage with the Proserv team, who is then working with the partner, so the partner is like prime to bring in Proserv resources to work on a customer engagement. This is very large enterprise, right? Where we need lots of developers very quickly. So they interchange between the partners developers and the Proserv developers. But that's when I start to take a hands off. I'll hand over the proof of concept and say, guys, this is what we built as a proof of concept. Now you go turn this into a production application. So it's very much, I just become like technical oversight. And then the Proserv guys step in and go, right, now we're building it out and working directly with the partner for the customer, which is different from obviously like Paul working directly with the customer. And so we'll obviously do a bit of coding, bit of proof of concept stuff. But to Matt's point, like all of us SAs have come from often a background or a history of engineering or infrastructure or whatever our sort of area of solutions architecture is. Yes, we're probably, I guess, a lot more senior in our our careers, but then that's where we work interchangeably with the Proserv teams to actually have that hands-on active. We might have been out of it for a little bit in terms of we're only doing proof of concept and not writing production code, but the Proserv guys, these are the guys who are writing the actual dev every day in, day out. That's what you guys do. So yeah, that's how we sort of the insight into AWS. That's how we all work together.
Yeah, and it's an incredible journey for you guys, right? Like, because I still think that like doing things hands-on is the way to learn fast, and you guys get the most experience out of all of us of doing that like day to day, right? In AWS land with actual customers, like hearing what they need on top of the AWS services that we're producing and scaling out across the board. So what I might do is let's bring the focus back on you guys. Tell us about the project that you've got in store around computer vision. How did it come to fruition? What it is exactly? Maybe we'll start there.
Cool. As we mentioned, a key focus of our team is machine learning, and I think a few of us on the team were interested in exploring computer vision. So we tried with building some simple models to detect things like cars, balls, red blood cells and white blood cells with openly available data sets. And I guess the next logical step was, can we count, let's say, the number of cars crossing a highway at a given point in time? So it's just playing around within the team. It's just a good exploration exercise for us to get started with machine learning, specifically computer vision. And by doing this sort of a mini project, we uncovered a few different ways of approaching the problem, how it can be solved. And there's a few other factors, caveats in counting, that we can explore. But it's sort of a project that can be applied to different domains as well. It's not just limited to highway counting. It can be a pedestrian intersection. It could be counting the number of plants using a drone. Very similar techniques apply, and it's very extendable to many use cases.
Should we give a bit of background of the original project, the sheep and cow counting?
Yes, we can. It is public information, so we can. So the team had engaged with a customer to work upon a project to count the number of sheeps initially at a given spot where there is a camera placed at the top and sheep sort of walk across. That is available when you search it up on Google. If you just look for AWS partnership sheep counting, it will show up. Um, yeah, that's the project that some of us on the team were engaged on. I was leading that project from the AWS side, and that's sort of where the interest stemmed from. I guess it's really cool project. See if we
Can
can
I
apply for use
ask an
cases.
important question? I think that the audience is very keen to know that if this AI is counting sheep, will the computer fall asleep?
Maybe.
Well, do computers dream of sheep in the first place, Aaron? Come
That's
on.
it. Yep.
Well, it
Electric
depends on the
dreams.
bias that's programmed into the model, right?
Do androids dream of sheep?
I
Yep.
felt as training the model, so
Yep. And I think Hello on Earth made a comment as well, which is like, sheep counting. That's snooze. I kind of lolled at that in the background, so that's great. So you guys haven't just been doing like counting of sheep, right? Like you've been doing a ton of stuff with counting. Should I bring up your screen just very quickly? Shall we have a quick nose, and then we can come back to like the why and the exploration that you had creating this? Just give everyone a bit of a taste of like what it is that you've created. Is that an okay way, or do you guys want to touch on that later?
Yeah, I think showed that Ishan is selling it a little bit short. So
Yeah.
Computer vision is kind of the root of it, essentially giving a camera capability to look at a picture or image and then digest information. But there's the simple idea of sheep counting makes sense. Show me a picture, detect a sheep. It makes sense.
Yep.
with cars.
But where this kind of engagement gets interesting is when you say you feed a stream, for example, you take the dimension of complexity and you make it harder. It's easy with patterns, with a model. If I show you a picture with 5 sheep, likely you would pick those 5 sheep out and say, this is the location. But now let me feed you a video of 10 frames per second of those sheep moving around. Now, isolated, it's easy to point out the sheep. But when you start moving sheep, you start introducing a problem of same sheep detection. The one sheep that starts from the right, moving to the left, should be detected as the same sheep.
I guess it's more complex with even cars, like at an intersection where you can have cars turning in different directions, not just going straight, but like doing a
And the
U-turn.
footage might cross over, right? Or the sheep might go behind a bush, or the camera's obscured, right? Yep.
Can be lost as well.
Exactly.
Like the model didn't pick it up, right?
Yeah,
Like,
and these are kind of measures you need to add on top.
Mhm.
So I think like he's selling it a bit short, but if you share the screen of the car demonstration, and I think it would be cool, like you use an algorithm in place to kind of predictively guess where the next frame would be, and then that would feed into information to suggest they were the same car.
I would also argue it's probably easier to do cows or cars, right? So you'd still need a substantial base level of photos, basically, right? to like a sheep at every angle, so that the machine learning algorithm still knows that's a sheep, even though it's moved to the left and it's like climbing upstairs or something like that, and obscured slightly by bush. But like at least cows have unique spots on them visibly, and at least cars have unique colors, number plates, and other things. So sheep are just like, they're either short and fluffy or short and shaved, right? And there are black sheeps, but it's most commonly you'll see like a white sheep, and it's really hard to tell that from another sheep if you're a farmer, outside of the tag that you might have on the sheep or the personalities of the sheep, which obviously you're not going to get through, like 15 seconds of video footage. Yeah.
So if you look at that as a kind of engineering or data science problem, like the points that you've mentioned are like difficult issues to solve, right? And so there's ways that you can get a solution to reduce the complexity so that you can kind of avoid, having to predict every case. So things like fixing the camera angle so that you're only looking at one angle of the shape, or just putting all the images in grayscale so that you can disregard the color, right? There's different techniques in terms of, convolutions on images to simplify images. There's different things we can do, right? So that we can reduce the scope of the problem and make it easier for us to solve. And as a result, generate like a high performing model.
Yeah.
On that note, Jeff, while I was doing some research regarding, counting stuff in videos, by stuff I mean it can be anything, like it's not generic to one specific thing. There's also ways of doing it without machine learning, which is basically, if there is a fixed camera, it compares the background and sees which pixels have changed, and then it tries to find an area that is changing, and it tracks it across the frames based on a certain history period. So like over the last 100 frames, if I have a fixed camera and this thing has moved from here to here, that is an object, but it wouldn't have the intelligence of, is it a car, is it a bike, is it a whatever else. But we need to also acknowledge that there are ways to do it without machine learning as well. But the stock standard,
well, that would be like a set group of pixels that remain like a similar-ish color moving across. Like we used to do this in like video game stuff beforehand, if we wanted like an artificial player to play the video game before like machine learning kind of caught on, right? The complexity with going down that route is it's really hard to say with a significant change to an object that's still the object, or if multiple colors cross over, and especially when the lighting in a scene changes and you've got shadows, it just like completely bombs out that particular approach, right? Which is why it's probably more viable to look at machine learning as a solution of computer vision to this.
Like you end up with big rules engines, right? Like before machine learning, any type of intelligence that we used to think was intelligence was effectively just big rules engines trying to work out what it was, rather than actual machine learning.
Yeah.
Before we dive too deep into the tech solution, I also just want to drive home like the value of what we've built. And so, the idea of like counting sheep, counting cattle, it sounds a bit like funny at first. If you think about it, it's like, it's like we're just kind of like doing it for the lols, right? But, there is immense value to, within like the agriculture industry. If you imagine like one cow is worth like, I don't know, $10,000. And, cows go missing all the time, whether they run away, they get stolen, eaten by a crocodile, whatever it may be. If you look at a herd of cattle, right? What's the difference between 1,000 cows and 900 cows? Like there's no real way for us to tell. And so by introducing this type of solution, although it seems like a kind of a simple problem, like there is actually immense value in something that we've built.
I was going to say very quickly, the other way that we do it in video games is if we needed to tape actors in real life and then transpose that on a 3D animated model, we would actually have to create these big white bubble things that would track as pixels, and then we'd guesstimate the transition that's needed for the animation to like move the bones animation like across to the same spaces as what we're seeing in the video footage. but it was literally like giant white bubbles attached to the person that was acting out in real life and videotaping. So sorry, Ishan, go ahead. It just reminded me of that other use case that we had, like pre-machine learning for the stuff.
Yeah. Maybe like we can dive in, and just to sort of dive into the technical aspects of it, what we did, but just to like, give other examples,
Mm-hmm.
not like, car counting, whatever is a boring job. It can be also used in medical areas, like are people wearing PPE correctly, things like that, or counting
Yep.
the number of people going in and out of a store rather than having a person outside, which I saw a lot of times. They just had a clicker and their job was to just one in, one out, one in, one
Concerts
out.
and festivals.
Festivals,
Yeah.
concerts, counting the number of people that are flowing through. Many other use cases as well. And it's a generic enough approach that you can sort of apply to other situations.
Yep. No, that's all good. And so you want me to share your screen very quickly on that, right? You've got something that's come up. Let me bring that up. Here we go.
Awesome. So we've prepared a couple of slides, just describing the approach, but we would love a lot of questions rather than me just presenting and walking through the slides.
Mm-hmm.
So it's a three-step process. At least that's how I can summarize this concept of counting things. The first step is actually finding the object. So the demo we are doing is based on cars. So actually drawing a box around the cars. And if you start off initially, no machine learning model would know what a car looks like. So the process involves around training a model that can recognize a car in this example. Luckily for us, like there is a lot of pre-trained models available. Ideally, like a good starting point is any model that's trained on the Coco data set, which is 80 different things like hat, remote, ball, bats, forks, knives, dishes. I don't know what else does it have. It does have a few of the animals as well, like dog. It has zebras for some reason. Yeah, it's got a wide variety of things, even a toothbrush.
Mm-hmm.
So the idea is for us to pick a pre-trained model because we do not have a very custom use case like, telling if a car is a Toyota versus like, Hyundai. A generic pre-trained model is what we picked in this demo, but obviously you can train your own object detection model. Essentially what you want from that model is given an image, give me the boxes of
Mm-hmm.
where what you are looking to count is. So just bounding boxes should be the output, and that's all we really need from step one. In step two, once you find a car or once you find the object that you want to count, you sort of assign it an ID. Like if I see Jeff for the first time, I know that's Jeff. And now that
Mm-hmm.
he disappears behind like a wall, I still know what Jeff is like. And when Jeff would reappear back, I can be, oh, that's Jeff. Okay. So the second step is assigning an ID to each of the detections and then keeping track of it, even across lost frames. In some problems, direction is important. So for that store counting example, how many people are in the store is basically how many walked in and walked out, the difference between them. So direction can be important as well, but in this scenario, like what we are going to be demoing, cars can be going in both directions and it's fine. And it should be able to handle that without making any assumptions. And the third thing is keep a running count based on the number of unique IDs that you have assigned. So that is essentially the count that you're looking for. And this process keeps repeating on the whole video when you process it one frame at a time. Any questions so far?
Do we have anything from the audience? And Paul and Aaron, anything that you'd like to kind of ask so far?
I think like for because I've seen some of the demos that Ish has taken me through, it's very clear in my head, and I think a lot of the dots will become connected once Ish starts going through and showing what is happening there and what a bounding box is and what that means and how it all stitches together. So I think the audience would be really keen to see like what it looks like, because there's so much use case for this all the time.
Cool. Let's then step through those steps. So the bounding boxes would look like these green boxes. In our example, I used a YOLO v5 model. YOLO stands for you only look once, but there's different types of models. There's mobile net single shot detectors. But the idea is whatever model you've chosen, it should give you the position of the object that you're trying to locate, whether that be a box, whether that be a center point. Ideally, the location is what we need.
So I guess like, why'd you go for YOLO versus like something like ResNet or something like that? Was it because you needed the speed and of an approximate guess, or was there more to it? Because I know YOLO is incredibly fast at kind of like putting everything into a boundary box, making a guess as to what it is, and then coming back with the data. Like, it's a very fast algorithm. I haven't used it since V3 or 4. It was like a while ago. But I know that there's other ones that probably make more of an accurate guess but take longer to process.
The YOLO model is pretty much the state of the art stuff in object detection. And I chose YOLO v5 because it's in Python, whereas YOLO v3 does involve compiling, I think, C code, which isn't entirely too bad, but I just wanted something that was easy to get started with in this particular use cases. But in more advanced use cases, the model that you've chosen matters a lot more compared to like something like cars, which is super generic. There's enough data available. I guess that was the reason. It's just super easy to train and super easy to set up. That's why I just went.
And I think it is very fast that if you start to look at like real-time video footage and you've got compute behind it, like it doesn't need to render and like continuously render the scene, making like more granular guesstimates, like, which is what I've seen with other ones as well. Did you experiment with other models, or you kind of you looked at the use case, knew you were potentially dealing with video, and then selected this model?
That's pretty much it, like the process you described, Matt. I did look at SSD models. The SSD model, similar enough, but I just found training the YOLO v5 on a custom data set. So what I tried was I tried training it on blood cells, so red blood cells, white blood cells, initially when I was learning this. And just to train the YOLO v5 versus the MobileNet SSD, this was much easier. I just went with it. And because it wasn't important to really have like the best model for the car use case, I think it did the job as well.
Cool. And probably the harder problem after selecting YOLO v5 is how do you tag each of these cars and then track it through video footage with objects blocking, etc. So like maybe let's have a look at like how you tackled that particular problem, right?
Yeah. In this case, right, we chose a pre-trained model. So that is trained on 80 different things. But let's say if you were training it for something else, let's say the examples of, I don't know, X-ray images and like finding a broken bone, for example, in it. It would involve labeling, drawing boxes by someone who is knowledgeable about it. So there can be very specialized labeling or something more generic, like can you please label all the laptops in the photo, which can be done by anyone without much expertise, but the medical stuff requires expertise. And the simplest solution to that was using ground truth and sending it to Mechanical Turk for simple use cases. But for the more advanced one, it's best if someone who is knowledgeable in that domain does it.
So
So what is I think we're going to ask the same question.
Yeah,
what is Mechanical Turk for everyone that might not know in the audience?
This was asked at my interview actually when I was
Yep.
commentating. And I said, "What is your favorite AWS service?" And I said, "Mechanical Turk." But he introduced it, so we're gonna let him explain it.
I would love to hear what you said in your interview, Paul.
Paul said in his interview, it is a guy that we hide underneath a chessboard using magnets to move chess pieces. Isn't that's the original Mechanical Turk, right?
Well, the original Mechanical Turk is that somebody invented a machine, and the machine was going to, like, I think it was chess, right? And playing against this machine, like, I mean, it was a long time ago, and the machine could win. But actually, what it was just a man hiding inside that machine playing against you, right? So it was just masqueraded as like some sort of machine that was able to play chess. But like, you know, our implementation of Mechanical Turk is to solve the exact problem that Ishan has talked about. When you have something that you can't necessarily solve with some sort of like computed algorithm, for example. There was a good example of this like a long time ago where I saw this was used and identified. So there was this job advertising site. I can't remember the specific details. And on this job advertising site, there was a bonus for people that would submit in jobs that might be advertised in brick and mortar environment. So online, there's a whole bunch of jobs that are listed. But if you see a job like out about in town, like let's just say your local hardware shop that had help wanted, call inside the shop, you could take a photo of that, which included the sign of the shop and where it was and the help wanted sign. And then that would turn into a digital online job that would be linked then back to that store. So this job searching platform would have lots of jobs that may not be listed in a digital format. Now, there will be specific jobs that might be listed out there that it's very difficult to determine like what the actual sign is and how to make the linkage between it, or it might be scribbled in, you know, what's it called, optical character recognition to convert it back into like specific text. So you want like an actual human to read it and make some interpretation around what is happening to be able to manually fill in the rest of the form to complete the forms, the job application for this specific instance here. Now, probably if you took a photo, like there's models out there that would, you know, can recognize like a specific set of address or recognize a logo or do pretty well at optical character recognition. But like a computer will do things in a certain way and it'll be very predictable. It'll do it in the same way all the time. Now, an interesting thing that happened with this instance was somebody had found like effectively a flaw in the system, which they said they made their own sign, put it as help wanted, went and stuck that sign on every single window, took lots of photos and was getting like $5 for each photo that they were submitting, right? So an automated computer-based process might not recognize that the sign is the exact same sign coming from the exact same person, just being like hounded on multiple different windows all over the place. And unless the computer algorithm is, you know, programmed to identify something like that, it's not. Whereas a human would be able to like identify, hang on a second, that's the exact same help sign that I saw before. So you can find it and exploit. That was Mechanical Turk was used to help them identify those things, but also the benefit of having like, you know, a human doing some of the classification there was able to identify things that a computer algorithm was not, because the computer algorithm is going to do exactly what it's told. But effectively, that's what you would do with Mechanical Turk. You would set something up to say, you know, I need something that we don't yet have a very good automated process around, or something that's very convoluted to design some sort of, you know, automated process around doing something. And we just want to be able to, you know, effectively crowdsource that to humans that will, you know, complete that task. And each one of those humans will be paid based on, you know, the tasks that they've committed and re-enter some data. And often that is around data classification type tasks.
Question, like, so on from Paul's mentioned OCR a few times, object character recognition. If you were to take this example, now obviously because you want to do like live streaming, right? You're not going to just be sending everything off the object character recognition everything off to Mechanical Turk to get people to go, that's what this object is. But if I was to assign you the task that instead of recognizing this vehicle, we want to actually recognize that number plate and read the value off that number plate, would you still use YOLO for that, or would you go about using a different algorithm?
What would you do, Jeff?
So AWS actually has a service exactly for that. It's called Textract. And
This is why I'm asking.
Yeah, little plug. So yeah, it does optical character recognition. And so you could feed Textract, this image, and it would be able to extract, the number plates. And so I guess to summarize what the task of optical character recognition actually is that when you feed in an image file, all of those characters are actually stored as pixels that the human eye can interpret, but a computer has no idea what it's actually looking at. And so when you run optical character recognition, essentially what it's doing is just converting those pixel characters into a string character that the computer can then process as text.
Yeah, and then to round that out to sort of what Paul was saying with Mechanical Turk, right? You can actually interact or integrate Mechanical Turk with Textract as well. So you would have your object recognition video running, which would then take a snapshot of the number plate, hand it off to Textract. If Textract wasn't able to actually derive the OCR, so couldn't get part of the number plate or something, then it can be sent off to a manual process, which could be Mechanical Turk, where somebody will go in and identify it by eye and then feed it back. So you could use a combination of what you've done here with Textract, with Mechanical Turk, to build out a full system, which might be used for, say, toll roads, or the police might use it for catching speeders or something. Like in a full end-to-end system, as opposed to just the object recognition part.
Yep, precisely. So that actually ties back into a very important concept within training machine learning models around evaluating your models. So how do you actually tell if your model's any good? So you could use a model like Textract or your own OCR model, but in order to evaluate the performance of that model, you can't just trust the characters that it's giving you are always correct. So you need some kind of ground truth, right? And so that's what something like Mechanical Turk is great for, because you can have a labeler, which you can treat as that is the source of truth, and you compare it to the performance of Textract or your OCR model to then verify that the characters you're getting are actually correct.
Yeah. Cool.
Very cool. Yeah, let's. This is the part that I was interested in, right? Because it's like this is the part where it's like it's guesstimating that it's a car, but has it smart enough to work out that same car is across footage. So talk us through this.
Sure. Yeah, like I mentioned earlier, the second step is assigning IDs. So in this case, you can see the first one is assigned 8, the other one's 9, the third one's 10, and as more come, it will increase. But the idea is, once you have assigned an ID to an object, you try and predict the future position using multiple methods. There are a few methods that we explored. And the idea is, in the upcoming frames, you search in the predicted location, see if that object exists. So if the car 9 is here, I'm expecting it to be somewhere here in the next few frames. So I look for that in the upcoming frames. And in the next frame, if I find a bounding box that very much overlaps what my prediction for where car 9 could be is, then I associate it to car 9. If a new car shows up in the third lane, I know I have not seen it before, so it assigns a new ID to it. So there's a few algorithms that I looked into when approaching the problem. The simplest one is computing the Euclidean distance, which is distance between the two centers. So if I have a detection, I see what cars I previously detected, and then I compute the distance from the center of what I have now to the previous cars, and the closest one is a match. given a certain threshold. Like if it's within, let's say, 200 pixels of it, it's the same one. But that approach can not be great if things are not moving in a straight direction. If things are moving across or around, that approach will very quickly like try and associate wrong things to wrong detections. Just because the distance can reduce, but it doesn't keep track of the movement or like the pattern in which it was moving. So if a thing is moving circular and coming, it doesn't account for that, it just accounts for the closest distance, which is where the other two algorithms are far superior compared to just taking the distance. And there are good research papers on sort and deep sort, but the idea is you feed it the bounding boxes and it gives you back unique IDs for each of the detections that you have fed it. So the idea is model gives you the boxes, you put that into sort or deep sort, and then it gives you back this is car one, this is car two, this is car three. And sort and deep sort of work how I described, where it anticipates the movement even based on like curves and stuff. So if I threw a ball up and I ran it on the sort algorithm, it would be predicting how the ball is falling, not just like the ball's going up, so expecting it to go up. Um, there are things like Kalman filter that come into these algorithms. I'm just mentioning a few things, but these are the two main algorithms that are pretty good for object tracking and are reasonably performant. Sort is quite performant over deep sort, but deep sort is its own machine learning model that tries to like, give unique IDs to each of the objects, whereas sort is mathematical based rather than having its own model.
So, well, I'm just like conscious of the time here. Do you think we could go into your live demo and show us some of the code and what it looks like and run some of that demo?
Yeah, let's do that. Let's do that. So,
And whilst I'm letting you prep, we did have Max Payne Life ask about, could we do this on a live Twitch stream? Yeah, we can actually. We had a live Twitch stream with some of the evangelists for Amplify over in the US. I think it was about 2 years ago, and the audience were asked to open up this web application that we'd made, and we were actually looking at the sentiment of facial expressions. If people authorize the web page to have access to their video cameras, everyone was cool with it because it was just a gimmick for a little conference. But then on our side, we had a screen that the audience could see that actually showed a pie chart with the amount of facial expressions that we're detecting, like people pulling sad faces or happy faces or crying. Like we saw all that in a nice pie chart, which was really, really fun. But YOLO can be used for real-time video as well as video footage that you've taped as well. It's a little bit of a different process, and it requires a bit more guts on the compute side. But I might point over to maybe Jeff or Ishan in terms of the complexities of real-time video coming in from a footage like a security camera or a live stream on Twitch versus like taking a movie file, right?
Just
I think
quickly, like when you have if you were to like just to answer Max Payne's question, he hasn't been able to Twitch stream into AWS Recognition ML. So to capture that stream and redirect that stream, like there's probably not a mechanism to do that. The way I would have done something like this is kind of like a bit of a hack around, which is I would just get OBS Studio. I'd create my own stream with OBS Studio. I'd have OBS Studio stream over the top of like my browser of the Twitch stream. Then I'd have OBS Studio push that Twitch stream to like Kinesis Video or something like that to capture it live. That would probably be the way that you would work around that. So let's go back to Ishan.
Awesome. I think you saw it running on the video with 2 cars. Now I've run it on a highway footage. You can see it's tracking like all the cars. And I'm also simulating dropped frames, which is pretty common if you're doing live streaming.
IoT device, right? Like the Raspberry Pi can't do 30 frames a second if you've got like a webcam at a certain resolution sometimes. Yep.
Exactly. So I've simulated that, and you can see all these colored boxes. So even if they disappear, it sort of associates it back to what the car was. So it doesn't duplicate count them. You can see like the model. I'll have to run it again. There's some interesting observations, like the cars in the top right corner, they're too small where my cursor is. But like the ones coming up in the other lanes are good. And as soon as it saw a big car there, it still detected it. So if you wanted to count all the cars here, you would have to improve your model to detect really small cars like this one that it has missed.
And that might be like that's one sort of solution to do it, but the other solution might be because it's not like this is the thing. It's not always make your model better. The model might be really great. Let's just fix the camera, make sure the camera angles to one side of the highway and a second camera for the other side of the highway. That might be an appropriate fix for it as well as maybe having a camera with like 3 times more resolution, for argument's sake. That might be able to identify it as well.
Yeah, and then another aspect as well with training machine learning models, when we think about like making the model better, oftentimes what that actually involves is just getting better labeled data, right? And so if all the training data that we're built our model on doesn't actually have instances where we have cars in the corner and boxes, like little boxes run around them, the model will never learn to actually detect those small edge cases where your cars are on like the edge of the screen. And so oftentimes, that is also a key to improving your model performance.
And just wanted perfect timing. Like I can highlight this example where you can see the label car, but it hadn't put a yellow box around it, which is basically it's waiting for the car to be seen for at least like, I think it's quarter of a second before I count it as a car. That's what that was. And then you saw them overlap and it was still 1 and 2, not like mixing them up. And now because they're going separate ways, it's a lot easier. Now you saw the first car is detected as a truck at times. So the counting algorithm also has to ignore those detections that are not persistent enough. Like it was only detected a truck for like 5 or 6 times out of like 100 times, which was a car. So it has to sort of scrap those away and not falsely detect that as well.
And what happens if you had 2 red cars that were the exact same model, and one was driving behind the other, and you've only got like this 2D footage, right? It's not going to be perfect all the time, but it's going to be close enough. Like I still think it would struggle with those situations, or happy to be proven wrong.
I reckon it depends on the ability of the model to recognize them as 2 separate cars, because the tracking and the counting algorithm relies on the accuracy of the model's boxes that it draws around the image. And in theory, you don't really need to stream the whole video for counting. All you need to stream is the bounding boxes, and then the counting can still work. So you can save some compute by running inference on the video and just streaming back the output of the model. And then that's more than enough to calculate the count. Yeah, I'm not sure if you would like a code walkthrough, but it's got certain threshold parameters. The general idea is if I go here in counted, I've got a loop running while the video has frames. It's randomly dropping, I think, 10% of the frames.
Why are you dropping frame rates? Is that just to improve performance? Because it's just pointless to every frame. Yep.
That too, and also simulate, like real world Raspberry Pi.
Yeah, or poor network connectivity over 3G or something.
Yep.
Yeah, and the first step is getting all the detections. So that's what that is. So it takes the input frame, formats it to how the model wants it as an input. You get the detections, you process the detections. So that's what the car label was. And then if it's not car, it just continues on. I had more logging here, but that's fine. And then you can see it's taking the tracker and sending in all the detections to the sort algorithm that I talked about, and it spits out a bunch of unique IDs and the coordinates. That's when you start seeing the boxes when the tracker is sure that this is 1, this is 2, this is 3. And the live count is essentially the length of the number of unique detections, which you can also see when the video is running. But yeah, that's pretty much the walkthrough of the code, I guess.
Very cool. We've got some people asking, is this on GitHub? I'm assuming probably not at the moment, right?
Not at the moment, but we can try and get something up on GitHub.
Yeah, maybe we can work towards getting something published on AWS samples.
Yeah.
That would be good.
Very cool. I always love this stuff. It's just fun to see computers try and guess things that we can guess easily, right? But very, very helpful for customers in solving problems where, you know, they don't have a cap. So I don't know, in Melbourne, I don't know what it's like in other cities, but like we've usually got like a strip on the road that like counts the crossover of like vehicles' tires like on it. That's like another way of solving this problem, but it doesn't work for sheep, right? Because yeah.
Have you tried where you're looking at the stream where you've got vehicles coming from different directions, but not from above, but from the side? So when a vehicle crosses in front of another vehicle, is it still recognizing it's the same vehicle once it's passed behind another vehicle? Yeah. Did you have any problems with that originally?
If you use the Euclidean distance approach, yeah, it will break.
Yeah.
But with these sort and deep sort algorithms, they're pretty good at that because
Yeah,
it's
cool.
the whole motion based on a history period, which can be the number of frames. So if the car has been moving, let's say in a C shape, I'm expecting it to continue that shape versus like the distance.
The other car doing something different. Yeah. Yep.
Cool. Did you ever check what percentage of frames you could drop and it still worked well? Did you test that, or did you just use 10%?
I tried it with about 70%, and it was still giving me good results for the project I was working on. I haven't tried it with the cars, but
yeah. And that probably comes down to, like, if you've got 30 frames per second, you could drop, if you were dropping 70% of that, that's still 6 frames per second, roughly. Like, that's probably enough easily to be able to track that. So it probably makes sense, and depends on the, the frame rate of what you're analyzing, and probably also like the detail, right? If you went to something that was like extremely fine detail, they might have a difference in that as well. But looking at a car, it's a pretty big thing.
Yeah, and the speed of movements, right? Like the velocity would probably make a difference. But I think of Mario, right? Like everyone knows that Mario is Mario, even though he's only like 4 frames a second in terms of animation, like way back in the old day. Yep.
Yeah. Very cool. Really interesting to see how machine learning transpires directly into something that, is usable. And then also to go back, Matt and I will say it all again, like, the use of Python behind there. Like, I think I quickly saw that the lines of code was like 236 lines of code. And there was a fair bit of boilerplate at the top, like configurations that were passed in there. Not a whole lot of code required to be able to produce some, really significant results out of the back of something like that.
Yeah, it's very concise.
Yep.
At times.
And secretly, probably a large amount of C++ under the hood. Yep.
Well, in those libraries, I'm sure that's probably all of those models.
It's all written in C++.
But Ishan, on the actual project, is that using a Kinesis video stream, or like how is the live video coming in? I assume it's not playing MP4 videos.
No, it would be at the moment we just have videos that we are running the model on,
Yep.
but it is done in a way to extend it to like different sources, whether that be Kinesis or a camera stream as well.
Oh yeah, like an RTSP stream or something.
Yes, IP cameras also.
Yep.
But yeah, the idea is change a couple of lines of code, and instead of a video, you can feed it from a camera source or your
Yep.
webcam as well. It's
Yep.
pretty open.
Yeah, cool. Yeah, when I did, like at Summit, we had the retail booth. I can't remember whether you guys were there, but that did a similar type of like looked through video and looked for a number plate on a car. The model was much weaker because all it was effectively doing was looking for objects, and if those objects happened to be a number plate, it sort of worked that way. But again, it was the same thing. You could push in a video, you could push in an IP camera stream, you could push in different types of streams or Kinesis video stream if you wanted to, and it worked the same way. So most of the libraries will handle any type of video input.
Yeah.
Cool. Well,
excellent. Yeah, go ahead, Paul.
I was just going to say we're like a couple minutes past. Like lots of questions today. Really like great overview. Would love to see some of that code come as a formally written blog post as an article stitched together from you guys. Thanks so much for sharing all the insights around Proserv and what you're doing day to day. And we hope to see you again sometime soon, guys.
Thanks, guys.
Thanks for joining us.
Thanks for having us.
We'll
Thanks,
catch
everyone.
everyone later. I'll end the stream now, but if you guys want to stick around, we'll talk in the behind the scenes. See everyone else though, and we'll look forward to Devs in the Shed same time next week with everyone. Catch you all. Bye.
Take care all. Bye.